All right, so now let's begin with number 11. Okay, so given, and the problem says, what can you tell about a function that is not continuous at 3, but the limit of f as x approaches 3 from the left-hand side is equal to the limit from the right-hand side? Okay, so that is a fairly restrictive piece of information, right? This pretty much doesn't give you a lot of choice. And the next thing is it's not continuous at 3. Okay, so how could that happen? Well, the fact that the f of x is approaching the same value, whether you approach it from the left or from the right, okay, that tells you that the picture has to look like this. So it could be continuous. If you have a continuous function here, certainly this would make sense. And in fact, if it is continuous, this condition has to be true. And if you look at the definition, whoops, I guess I'm going to just undo a little bit of a thing in here. All right, so we're still having missing something in here, okay? But the fact is, if you look up the definition of continuity, it says the value f, if f were continuous at 3, then f of 3 has to be defined, okay? F of x has to be defined at 3, and the limit has to exist, which means that this has to be true. And this limit value has to be equal to f of 3. Now, it's not continuous, so that last condition, f of 3 is equal to this limit, the value is equal to the limit, cannot hold if f is not continuous at 3. So that means f of 3 cannot be whatever this limit is. The limit in this picture has to be this value, but f of 3 cannot be there. Maybe it's down here, okay? Maybe it's up here. We don't know, but the point is, because f of x is not continuous at 3, the limit has to be different from f of 3. All right, so that is what we can conclude. Therefore, these 3 dots mean, therefore, the f of 3 cannot possibly be equal to the limit at x is equal to 3, or as x approaches 3. All right, so, and the only way that could happen is that there is a hole at x is equal to 3. The picture pretty much have to look like this, okay, where you have a circle here, an open circle, and then the value of the function at 3 has to be something besides that L value, which is a limit value from the left and the right that is equal to each other. Okay. Number 12 says, find the derivative y prime. By the way, y prime is also denoted with dy dx, and that's what you are supposed to find. Now, this one also says your answer may include y. Okay, now why is that true? Well, because if you look at this, it's hard to solve this for y, right? You can't really write it in this way. If you could do that, then you can do your explicit differentiation, but that is not possible here because you have 2 terms involving y, and you have y and y cubed. And so what we have to do here is to carry out that implicit differentiation, right? That's the first thing you should notice. The problem does not say explicitly that you are to carry out implicit differentiation, but you should know that's the only way to do this problem, because you cannot write y is equal to something explicitly. All right, so what does implicit differentiation involve? Well, x squared just becomes 2x. Okay, we are implicitly differentiating with respect to the independent variable x. Now 5y becomes 5 times the derivative of y, and this is what happens with implicit differentiation. What happens to y cubed? Well, y cubed, see, the thing is, when we do things like that, we are thinking of y still, at least locally, as a function of x. So when they say y cubed, this is what we are talking about. So that becomes 3y squared times the derivative of the inside function, which is y prime. And of course, that is what we are after, right? Oh, 25 just becomes 0. And so that is what we have. And then now we just solve this for y prime. Okay, so what do we have? Let's factor out y prime on this side here. You have 3y squared minus 5, and these come from this term and this term, both of which have y prime, right? So you factor out y prime. I switch the order because I don't like to start the expression inside the parentheses with a -5. So it's 3y squared minus 5. Okay, now on the other hand, I can move this, I can subtract 2x from both sides, and this is what we have. And so y prime, which I want you to start writing dy dx because that is more precise in many situations. Sometimes the x is called t or theta or something, right? So let's say in this case, it's dy dx, which is -2x all over 3y squared minus 5. And that is going to be your answer. Now you can switch this if you like, 2x, you can change the sign, 5 minus 3y squared, that's of course acceptable. And if you happen to know, see, I don't know what this curve looks like, the curve that would satisfy this equation here. Okay, what kind of curve is it? I really have no idea. Okay, when you have y cubed and x squared, it's going to be some kind of a curve, right? And if you can find one point, which is xy, which satisfies this equation, then what this is telling us is that's going to tell us the slope of the line tangent to this curve at that point xy, simply by plugging in the x and y values here. Then this expression will give you the slope of this line tangent to the curve at that point. And so that's how you apply implicit differentiation. Okay, similar to that is the idea of logarithmic differentiation, which is number 13. Okay, let's take a look at number 13 and look at this question on the logarithmic differentiation. To find the derivative, which is y prime, what we have is an explicit function. Y is 2x plus 1 raised to the x power. Notice here, I have x as a part of the base and also the exponent. This is exactly where you would have to apply logarithmic differentiation, because you really, again, have no other choice, all right? There's no formula that would let you find y prime directly, right? All right, so the first thing you have to do is to bring this x down from the high, lofty, esteemed position of an exponent into everyday life to make him or it into a commoner on the same level as everybody else, right? And the way to do that is our fancy tool, logarithmic function, and the natural log function, which is the easiest one to differentiate. Okay, so natural log of y is, of course, the natural log of this expression. But what happens when you apply log? Well, the exponent becomes a coefficient. Okay, that is the nicest thing. It could be the weirdest thing, but it's also the nicest thing about a logarithmic functions. Okay, so that's what you get. The ln of y is this. Now we do the implicit differentiation, and every logarithmic differentiation question is technically just take the log of both sides and then you do the implicit differentiation. Now, what happens to the left-hand side when you differentiate this? Well, it just becomes 1 over y, because that's the derivative of the natural log function. And then, of course, you have to do y prime, and due to the chain rule. Okay, now we take this expression, that's a product. So we take the derivative of the first times the second plus first times the derivative of the second, which is 2x plus 1 in the denominator. And then you have to multiply this by the derivative of the inside function, which is 2. So let's go ahead and write this again. 1 over y prime, 1 over y times y prime is equal to log of 2x plus 1 plus 2x all over 2x plus 1. Okay, so that gives you the answer. Y prime, which you can also write as dy dx, is y times all this, right? So here's what I'm going to do. I'm going to multiply both sides by y. This whole thing has to be multiplied by y on the right-hand side. Of course, these will cancel. what you will be left with is simply that times y. Okay, so what was y though? Y was this thing. Okay, so the answer, I'm going to write the y in front. It's going to be 2x plus 1 to the x power, that is y. And then multiplied by this enormous expression, the natural log of 2x plus 1 plus 2x over quantity 2x plus 1. Okay, now it sounds and it looks pretty bad, right? But don't let that intimidate you. If you are given any x, then you can find the derivative at this point by evaluating this expression. And that is a lot. You could do that only because you knew how to apply the natural log and implicitly differentiate both sides. All right, let's go to number 14. Find the equation of the line tangent to this function, which is e to the 2x plus 1 to the third power at 0, 8. So the claim or the assumption is that this function is supposed to go through this 0, 8, the point 0, 8, and then it's going to have some sort of a curve, right? It's a smooth function, and we are supposed to find this line, the tangent line, or the line tangent to this curve at the point 0, 8. Now I just drew it as if the tangent has a positive slope, but we don't know that yet, right? So that's what we need to find out. All right, so what do I have to do? Oh, by the way, is that true? I mean, the assumption is because this is a question that's asked in the practice test, you would assume that this is a well-written question, right? That this line, this f clearly or is supposed to go through the point 0, 8. Let's just check first to make sure that this is a doable question. You don't have to do that, but I think it's important for you to know that the problem is doable before you start. Okay, so when you plug in 0 for x, you have e to the 0th power plus 1 to the 3rd power, and of course that's 1 plus 1, that's 2 to the 3rd power, which is 8. So yes, this graph does go through 0, 8, and now we can start the problem. Take the derivative. That's 3 e to the 2x plus 1. That's the chunk, the blob inside. And then you square it. And then, of course, do not forget to multiply this by the derivative of the inside function, which is 2 e to the 2x, right? Okay, so let's combine the terms here. It's 6 e to the 2x times e to the 2x plus 1 squared. All right. Evaluate this at the point 0 when x is equal to 0, because that would be the slope of this tangent line. 6 times e to the 0, e to the 0 plus 1 squared. That's 6 times 1 times, now that's going to be 2 squared, and that's 24. So my, by the way, this is your slope of the tangent line. Okay, so my graph was, yeah, sure, the tangent line has a positive slope, but it turns out to be much, much steeper, right? The slope is much greater than what appears on this graph. It's 24. So once you go 1 unit to the right, and the graph will go up 24 units. Okay, so how do you write the line, the equation of the line, through the point 0, 8 with a slope of 24 is going to be y minus the y coordinate of the point is equal to slope times x minus the x value of the point, right? So this is just 24x, and so y is 24x plus 8. Clearly, this one goes through 0, 8, and this will, by the way, give you a linear approximation of sometimes called a linearization or a linear approximation of this function f at points close to 0, 8. Okay, so that's how you can use that if you are interested in linear approximation. This problem does not ask you to do that, but that's the same thing. Okay, let's do number 15, and then we will go into the next segment of this video. For the function below, and the function below is x cubed minus 3x minus 1. Okay, so what about that? This is a long problem, so let's be prepared for that. And in fact, I need more space, so I'm going to append a page in the same graph paper format because I will need some space. Okay, for this function below, find all local extrema and inflection point or points, if there are any. Find the intervals where the function is increasing and or decreasing, and graph the function. All right, so this type of question is going to be worth a lot of points, probably 10 or more points on your final. Remember, you had a 20-point question in one of those exams. All right, so what do you have to do? Well, for any of these local extrema and increase and decreasing and graphing, it really helps if you know the derivative, right? By the way, you can find other things too, like for instance, f of 0 is going to be what? -1, just plugging in 0. Well, that's your y-intercept, right? So that's the kind of thing that you can also do before you start taking the derivative and so on. But if you do take the derivative, that's 3x squared minus 3. That's nice because that's factorable. It's 3. Well, okay, so let's take out 3. That's 3 times quantity x squared minus 1. That's 3x plus 1, x minus 1, right? Now, to find the local extrema, what you want to do, oh, by the way, this is a polynomial. The graph is going to look like this. That's your end behavior. And it's defined for every single point. Because it's a polynomial, you should know this, by the way, every polynomial function is continuous everywhere, differentiable everywhere, and the end behavior. So this is going to be a nice thing. So you don't have to worry about vertical asymptotes or horizontal asymptotes or lateral or oblique asymptotes for any of these polynomial functions. Okay, so you want to set this equal to 0 at where? Well, you set this equal to 0. 3 times x plus 1, x minus 1 is equal to 0. X has to be plus or minus 1. And these are the only critical points. We have found all of the critical points. All right, now, how do you find if these are local maxima or minima? Do they have to be local maximum and local minimum points? No, the answer is no, they may not be. Okay, but if there are any local extrema, then they would have to happen at this point. All right, so this is a great time to do the sign chart. These are -1 and +1. These are the two critical points, right? F prime, which is, oh, I'm going to just do that. X plus 1, x minus 1. And then, of course, the derivative is 3 times the product. And the sign doesn't change, so I can just go with that. So x plus 1 is going to be negative here, becomes 0 when x is exactly -1. And after that, it's going to stay positive, right? Whether x is between -1 and 1, exactly 1, or greater than 1. X minus 1, on the other hand, is negative here. And when x is -1, that's still negative because it's -2. If x is anything less than 1, this will stay negative. And when x is exactly 1, this becomes 0. And then when x is greater than 1, it becomes positive. So now for this interval from -infinity to -1, negative times negative is positive. 0 times anything is 0. Negative times positive times negative is negative, and then 0 and positive. Okay, this is great. Okay, this is I highly recommend if you have not learned how to draw a sign chart or a sign table, you need to learn this. Okay, because this is the best way to figure out where the function is increasing and decreasing. And you can even do a little picture. See, this is 0, this is down here, and then this is 0, and this is going to go up, right? So clearly, you can see that this is a maximum. It's a local maximum, and there's local minimum. All right, so let's go ahead and figure this out. What is f of -1? Now, remember, my function was, let's go ahead and write this down again, x cubed minus 3x minus 1. So if you plug in -1, you get a negative 1 to the third power minus 3 negative 1 minus 1. And that's negative 1 plus 3 minus 1, and that is 1. F of 1 happens to be 1 cubed minus 3 minus 1, and so that is negative 3. Okay, so all of this is going to tell you that, oh, by the way, I used what is called the first derivative test, right? So you have a critical point, and at that critical point, if the derivative goes from positive to negative, then you have a local maximum. So you have a local maximum at x is equal to negative 1, and also the value, the local maximum value happens to be 1 at that point. Now you also have a local minimum. Where is that? That's at 1, and the value of the local minimum is negative 3. Now for these questions, I would just take it if you just find the x coordinates. You can say the local maximum occurs at negative 1, local minimum occurs at 1. That would be sufficient, generally speaking, unless you are specifically asked for the values of the local max and local min. All right. You could also use the second derivative test. And in fact, because we have to find the inflection point, let's go ahead and take the second derivative. All right, so I found this, the first derivative, that's 3x squared minus 3. 3x squared minus 3 without factoring, okay, because that's easier to differentiate to find the second derivative, which is 6x, right? And that's it. So here you can do a very simple table. This is the second derivative. Well, 6x is negative here, 0 here, positive here, right? I mean, this is positive if and only if x is positive, okay? So that means you have a inflection point. Okay, so what's f of 0? Well, that was negative 1, and that is the inflection point. And in fact, there's only one inflection point. If somebody says, no, I found another inflection point way up there when x is nearly a million or something, and you say, no, you could not have, and that's wrong, because what do you know about the inflection point? Well, by definition, an inflection point is where the concavity changes. This is concave down here, and this is concave up. I should actually go ahead and write this. All right, so f is concave down on from negative infinity to 0, and concave up on 0 to infinity. We have already established where it's increasing and decreasing, right? And so those are some of the things that we would know to help us graph this. Now, do we answer all the questions except graphing? I found the local extrema, right? So those are the only two. By the way, we know those are the only two, one local max and one local min, because there are only two critical points, right? No other points will have local max or min, because every local extremum has to happen at a critical point. The vice versa is not true. Not every point, not every critical point represents a local extremum. Inflection point, we found that intervals of increasing and decreasing we found. The only thing missing is the graphing, right? But we already have a lot of information, negative 1, 1. So let me go ahead and pick a plot certain points, okay? Give me just a second. Okay, so we already know 3 points. We know that negative 1, 1 is a local maximum. So it has to start to go down this way, right? And then this is an inflection point at 0, negative 1. And up until this point, the concavity is down, so it has to look this way. And at this point, you start to steer, if you're driving this way here, you're steering to the right. And this point, you start to steer to the left. And this is the minimum point, local minimum. And then after that, it has to continue to increase, and in such a way that the concavity is positive, which means it has to keep increasing faster and faster. So we don't know this point here. We haven't found this yet. We don't need to. And nor do I know this point. These are the two zeros of this polynomial function. We don't need to know that. But we do know that this point is 1, negative 3, and this is negative 1, 1, and the inflection point here is, let's go it this way. The inflection point is 0, -1, which also happens to be the y intercept, right? And so this is a good enough graph to express or to indicate all the important points of this graph. This is going to be a continuous and smooth function because it's a polynomial. And so that would be your answer. And it is consistent. The end behavior, remember, has to go this way. And it is consistent with end behavior, which we already knew at the beginning. Okay, so that is number 15. And I will go on to the next segment of the video to start with number 16. All right.